Hi everyone, Assalamu alaikum warahmatullah. Welcome to the sixth lecture of our subject mechanical vibrations. So today we are going to discuss about the Laplace transformation. Up till now we have been solving the dynamic systems and the mechanically vibrating systems using the general solution method of differential equation, and which we have seen is quite long, lengthy. It's sometimes becomes quite messy, but in this lecture we are going to look at into another technique, that's a Laplace transformation, which is quite compact compared to the previous method, and it is used for different purpose, not exactly the same purpose as for the general solution method, but we can use the Laplace transformation for that purpose, for which we use a general solution as well. So today we will just look into the mathematical and physical side of the Laplace transformation and just cover some questions. So in this lecture we are going to focus on understanding what Laplace transform is and why it is used. So we'll just try to understand physical intuitive meaning, what's happening behind those equations, and perform some Laplace transformation of some common time functions, solve some systems, and select a problem, and we will simultaneously solve it using the general solution method and using the Laplace method, and we'll try to reach the same conclusion, just to show you how much work will be reduced if we use the Laplace transformation. So jumping on to the what Laplace transformation actually is. So Laplace transformation is an operational method. It's a mathematical tool that can be used to solve the linear systems, uh, that is primarily used to solve linear systems, time invariant systems. We have discussed in detail what these are. What does it mean by linear system? What does it mean by time invariant systems? Uh, and time invariant differential equations. You can say time invariant differential equations. So this is the main part. Although we can solve the non-linear systems as well, but we have to convert that non-linear system into the linear system, and then we can apply the Laplace transformation on that. So what it does, uh, it converts differential equation into algebraic equation, and then it solves the system. And how do we do it? We do it by using a Laplace very complex variable. That's called the complex variable. There are many other purpose for using the Laplace transformation as well. Uh, like as we have seen in the what is the difference from general solution method. So general solution method is becomes quite messy when we don't have a simple force. Up till now, the system we solved was a simple force that was being applied. Either we use a simple force or we use a simple harmonic force. We haven't seen the ramp force, we haven't seen the impulse, we haven't seen the step force. For the general solution method, we only what we saw is the harmonic forces, which is comparatively easy, and it becomes even messier when it's multi-degree of freedom, and at compared to that, the Laplace transformation is easier for that one. So the general solution method, as we have discussed, it deals with differential equation. while the Laplace deals with algebraic equation. We have to apply initial conditions in this one. It is included in the solution in the case of Laplace. Uh, difficult for it's difficult for all forces. We can say various forces. And this can handle any force function. The Laplace it can handle any type of force function. And again, it doesn't deal with the multi-degree of freedom, while the Laplace deals with the multi-degree of freedom. That's the general solution method. General solution method, GSM. Okay. So that was just a brief difference between the Laplace transformation and the differential solution method. What this complex variable is? This complex variable is actually a combination of this sigma plus iota omega. Iota, it's a imaginary number. So another thing, as we have seen in the general solution method, in general solution method, we have to solve transient and steady state separately. Transient and steady state solution separately, while in Laplace transformation it solves for transient and steady state simultaneously. So it solves both. We don't, like, if you remember, in the general solution method we have to solve the homogeneous solution and the particular solution separately, as we have seen in the last lecture, while this Laplace transformation will solve both of them together at the same time. Why is that so? Because the Laplace complex variable s here, it's equal to sigma plus iota omega, where sigma represents the growth or the decay of the vibration, while omega represents the oscillations. And if you see any general vibration behavior, so it's always like, maybe it starts like this and it keeps on increasing and then it achieves a constant vibration amplitude. So this growth, this part is called transient, and once it achieves the constant amplitude, becomes steady state, this part is called steady state. So if you want to solve this vibration using the general solution method, we have to use the homogeneous solution for this part, and we have to solve this one using the particular solution, if you remember. So but in the case of the Laplace transformation, this growth or decay is represented by this real part sigma. This part is represented by sigma, and this oscillation, this represents this steady state part of the solution. So again, you see how it combines both the transient and the steady state behavior together. It captures both of them together in the same solution. Now let's jump into the physical intuition of what does it mean by the Laplace transformation. So the Laplace transformation converts the motion of any system into its information. Like in the time domain, you are mainly concerned with where is the vibration at particular time period.